Alright, this is LeetCoding in JavaScript. We're tackling LeetCode number 72, edit distance or Levenshtein distance. This is a dynamic programming problem. It's a hard problem. It's one of those problems you definitely can't just jump right in and code. You got to write it down on a piece of paper and try to extrapolate a broader algorithm from those patterns. So let's jump right into it. Given two strings, string 1 and string 2, find the minimum number of operations required to convert string 1 to string 2. Given the following operations, insert a character, delete a character, or replace a character. So we have two string examples here. J, Rock, and Shrek. Just, right off the top of your head, if you said two operations, you'd be correct. So J and O we can replace with T and E, and that would satisfy these conditions. All right, so give this one a shot. Pause it, take 20 to 30 minutes and try and tackle this problem on your own. And then we'll go through the theory side. We'll also have breakpoints inside the theory side, trying to get you to come up with your own algorithm. And then we'll jump right into the code and the implementation. All right? Okay, so theory side. This is a dynamic programming problem. So the whole idea of DP problems are we're breaking up a larger, broader problem into smaller chunks that are manageable, and our current decision is being informed by our previous decisions. And a common way to handle this is with a matrix. So let's look at our matrix here, our shell scripts. All right, so this whole idea is we're tracking string 1 as this row here, and string 2 as our column. And we're breaking it up, and we're saying at any given point, what would it take, how many operations would it take for string 1 at this point to become this string 2 at this point? That's a little esoteric and kind of vague, but we'll jump right into it, and I think you'll get it fairly quickly. Okay, so in this first grid number, how many operations would it take for this empty string to become this empty string? Well, that's simple. That's just 0 operations. Second column. How many operations would it take for the combination of this empty string and J to become an empty string? Well, that's just one deletion of J, so one operation. Likewise, empty string J and R to an empty string, that's 2 deletions. And so on and so on. So JRO, that's 3 deletions to become this empty string. JROK, that's 4 operations. 4 operations to become this empty string. All right, second row. How many operations would it take for this empty string to become T and this empty string? So that's one deletion of T or one insertion of T on this row. So that's one operation. How many operations would it take for J in an empty string to become T in an empty string? That's just one operation, right? One replacement of J to T. Continuing, JR in an empty string to T in an empty string. That's 2 operations, one replacement, one deletion. JROK in an empty string to T in an empty string. That's 3 operations, right? 1 replacement, 2 deletions. And finally, likewise, JROK in an empty string to T in an empty string. That's 4 operations. 4 operations. 1 replacement, 3 deletions. Okay, so let me just address one thing real quick. Why do we have this empty string here? We've added this empty string as like a buffer or like a 0th index of this grid. And you'll see why it's important to have that in a second once we go through the algorithm implementation. But just take it as fact now that we need this right here. Okay, so we've filled out quite a bit, and maybe we'll go through a little bit more examples here. So R and T in an empty string to an empty string, that's 2 deletions. R and T to an RT in an empty string to J in an empty string, right? That's 1 replacement and 1 deletion, so that's 2 operations. All right, so from here we've got about 50% of the matrix filled in. Try and pause the video, see if you can come up with a pattern that's going on here. I'll give you a hint. So at any point, at any index, at any grid index that we're trying to fill in, try and deduce a pattern from the previous either column -1, row -1, or caddy corner value, column and row -1, right? So if I was trying to fill in this value right here, X, I want to find a pattern that relates this number, the amount of operations it takes, to these 3, or one of these 3. So pause the video, give that a shot, and we'll come back, and that will be our first part of our algorithm. Okay, so if you deduced that we were looking at the minimum value of these 3 and incrementing it and adding 1, you'd be correct, right? So what we did here is, if we filled in these values, we said, okay, we'll take the minimum value, or maybe you said 1 before it, or the caddy corner value, whichever the minimum value was, we'll take that one and we'll increment it to 2, right? So our minimum value here was 1, and we'll increment it to 2. And you'll see that every single value on this table that we currently have follows that rule. Maybe it's not that clear. Maybe you need to come up with a few more examples and prove that to yourself in an interview situation. Just go through a couple of test cases, but that's pretty much what you'd get. Okay, there is one spot where this doesn't hold, and we'll see that right now. So let's test RT in an empty string to RJ in an empty string. All right, so how many operations would that take? Well, that would just take 1 replacement, right? I can just replace J with T, and I'd have empty string T and R compared to empty string T and R. Now this doesn't follow our rule. So in our previous part of our criteria algorithm would be find the minimum value, which of these 3, right? Row -1, column -1, or both, caddy corner value, and then increment that value. So in this case, it would be our minimum value would be 1. We'll increment it to 2. So this value should be 2, but we've just proved that it's really 1, right? We just replace J with T. So what's going on here? What can we add to our algorithm? Pause the video, try and figure this one out. Okay, so our second check to our algorithm should be if at the index that we're at, the grid value here, right? This X of I, J, right? At this grid value, if our string value, our string 1 value is equal to our string 2 value, what we're going to do is just take the caddy corner value and set it equal to our current grid value. So say that one more time. If R is equal to R, or our string 1 index is equal to our string 2 index, at the grid index that we're at, we'll set the column -1, row -1 of the grid value, or this caddy corner value, equal to our grid value. Those are a lot of words, but just follow along with what I'm doing here. That should make sense. All right, so we've got our algorithm here. If this equals this, take the caddy corner value, else we'll take the minimum value of all 3 of the previous data points, and we'll increment that value. So given that algorithm, try and fill in the rest of this grid. Just using that algorithm, not checking, not sanity checking at all, okay? All right, so let's do that. So our first check is R equal to O? No, it's not. So we'll take the minimum value of these three and we'll increment it. So our minimum value is 1. We'll increment it to 2. Is R equal to K? No, it's not. We'll take the minimum value and increment it to 3. Is E equal to empty string? No, it's not. We'll take the minimum value, which is 2 here, our only option, and we'll increment it. Is E equal to J? No, it's not. We'll take the minimum value and increment it. Is R equal to E? No, it's not. We'll take the minimum value, which is 1, and we'll increment it. Is O equal to E? No, it's not. We'll take the minimum value, which is again 1, and we'll increment it. And let's pause here for a second and say, why are we allowed to compare our current value to these previous three values? Well, the whole idea is we're taking chunks and we're adding another layer every single time. So we're informing our current decision with the past decisions, and because it's a two-dimensional matrix, we have three options here, right? Try and prove that to yourself. Like, why are we able to compare this with this state, or given this grid value? You know, why can we make a decision based on all three of these values instead of just one, right? Why are we able to take the minimum value of these three? Walk that through. I'm pretty sure you can prove that to yourself. Well, let's finish this. So is E equal to K? No, it's not. We'll take the minimum value and we'll increment it to 3. Is K equal to empty string? No, it's not. We'll take the minimum value, which is 3, and increment it to 4. Is K equal to J? No, it's not. We'll take the minimum value, which is 3, and we'll increment it. Is K equal to R? No, it's not. We'll take the minimum value, which is 2, and we'll increment it to 3. Is O equal to K? No, it's not. We'll take the minimum value, which is 2, and increment it to 3. Is K equal to K? Yes, it is. We'll take the catty corner value, or the column minus 1 value, row minus 1 value, and we'll set it equal to our current grid value, which is 2. Right, so at the end of this, we'll just return our final grid value, which is the final comparison of the entire length of this string and the entire length of this string. And we can do this. We can take this entire length, including this empty string, because this empty string is not informing the rest of our grid, right? If this was maybe 1, then yes, it would inform our final value, but it's not. It's 0. So it really has no effect on our existing values. Right, so that's the algorithm, and that's kind of the theory behind this. Pause the video again, try and code it up in JavaScript, and then we'll code it up as well in a few seconds. Right, so let's code it up. Okay, so we'll have a string 1 input, a string 2 input. What's the first thing we want to do? We want to create this grid. We want to create this shell grid or this matrix so we can start putting in our values and comparing those values and implementing our algorithm with this matrix. So what is a matrix? Well, I'll actually do const here. A matrix, if you recall from linear algebra, is really just a nested array, right? A two-dimensional matrix could be said to be like this, right? Right. This is a 3x3 matrix, a two-dimensional matrix. Doesn't look like it. It looks like a 1x3, but it could also look like this. So that's a little bit cleaner, more obvious to be a 3x3. So linear algebra, if this two-dimensional array is really, or this two-dimensional matrix is really just a nested array, and every time we nest another array, we're adding a dimension into our matrix. So that's what we're going to do. So our const grid here is our parent array, and we're just going to populate it with inner arrays. So and it's going to be of length string 1. So string 1 is going to be our row, or rather, it's going to be our column, and we're going to populate it with rows. And we're going to add an additional index here for our empty string. I'm missing a lot of things here. Okay, so let's instantiate some rows. And again, those are going to be arrays as well. And then we'll populate those rows with just some values, right? This is going to be of length of our string 2 plus 1 for our empty array, or sorry, empty string. And we'll simply push just some values, and we'll keep them tracked by j. Outside of this inner for loop, we'll instantiate our first element of our row to be I, just to keep track of everything, right? We can keep track of every single row by this outer array or outer for loop. And then we'll simply push our rows to our grid. All right, so that should be our shell matrix that we're going to implement our algorithm on. Just to prove it, we'll console log our grid, and you'll see that we do in fact have a matrix here, and it has the same inner dimensions of our matrix in our 3 section. Right. So let's implement our algorithm. So what is our algorithm? Our algorithm really is we're looping through every single element of our matrix, which is every single for every single row we want to loop through every single element in every row. So that's already a nested for loop. And we're starting at the first index or the second element because our first or our 0th index is our empty string. All right, what do we want to say? Our first check would be, is our string 1 value equal to our string 2 value at this current index? If so, then we'll simply set our current grid value to the catty corner grid value. So if string 1 current index, which would be I minus 1, is equal to string 2 current index, which is j minus 1. All right, so prove this to yourself. Prove that this is our current index. Walking through, we've started some indexes weird, we've added some indexes, so just prove that this is actually our current index, current character that we're comparing. If this is true, our current grid value will be our catty corner grid value. And if that's not true, we will take the minimum value of the previous 3 values and we'll increment it. So else our grid value, our current grid value, is the incremental value, so 1 plus the minimum value of our previous 3 values. So it's either going to be the minimum value is either going to be the catty corner value. It's either going to be the row minus 1 value, or it's going to be the column minus 1 value. And that should take care of our algorithm. And at the end of this, we're going to return our grid, or our final grid value. which happens to be string 1.length and string 2.length. And then we're also going to console log our grid to compare it to what we previously had. Let's clear my output and run it again. Okay, so you'll see that our final grid value is 2, and going through our matrix just like we did previously in the theory section. So 0, 1, 2, 3, 4, 1, 1, 2, 3, 4, 2, 2, 1, 2, 3, 3, 3, 2, 2, 3, 4, 4, 3, 3, 2. That's correct. So our algorithm works, and our final output is 2, which is also correct. Great. So that was Levenshtein distance. Great little dynamic programming problem. I think it's a little bit on the hard side for dynamic programming problems or LeetCode problems in general. It is a LeetCode hard problem. But if you can get this, if you understand the concepts and understand why we did what we did and kind of the mindset on how to solve this type of problem, I think any dynamic programming problem is well within reach. So as like a mission 2 to this problem, what if I took away your ability to replace a character? So you only could insert a character or delete a character. How does this inform your matrix? And consequently, how does it inform your final algorithm? So it does so subtly, but how I would go about doing this, how I would recommend it to you is, again, go through this entire matrix, fill it in, extrapolate some sort of pattern, test that pattern on the other half of the matrix and see if it holds water. Maybe change some of these test cases. Try out your own test cases with more of equal values. Make this E or something like that, and then implement the algorithm from there. So again, you don't have the ability to replace a character. You can only insert and delete a character. So in this case, we can't replace J with T. We can only delete J and then insert T. So that's 2 operations instead of 1 operation here. Or sorry, not here, here. Oh, messed up my grid. Right, so let me know in the description if you get it, or the comments if you get that problem, and I'll see you in the next one.